So in part one, we were asked to draw the graph for the circuit diagram, considering this is an op-amp amplifying it. So as you can see here, there's no feedback, which means rule 2 doesn't hold, which states that the voltage across the two would be equal because there's no feedback to make it equal. In other words, if this is V1 and this is 0, then what's the difference? The difference is negative V1, because 0 minus V1 is going to be negative V1. So this is going to be inverted. And you can see that because this V1 is connected to the inverting input, the negative. We have plus and minus 15 volts in, so that should be our maximum, but the question states that saturation would be at 13 and negative 13. So it's almost the same anyway. So we're given the equation of the input, which is 0.5 volts, amplitude, 0.5 volts. It's a sinusoidal function, so we have the omega t, but omega is 2 pi f, and nicely they have left the 2 pi out. So we know that our frequency is 50 hertz, which means our period is 0.2. If you inverse that, you get 0.02. So that's our period, seconds. So if this is our graph, then our equivalent graph would be the inverse of it. But the thing is, the op-amp has an amplification of sometimes 10 to the 6. So if you take 0.5 volts and multiply that by a million, you're way off the maximum of a 13 volts. Way off. So the scale for this kind of graph would be probably right here. This would probably be the 13 volts. The negative 13 volts. And this would probably be the 13 volts. In other words, saturation will be reached at this level, if it's drawn accurately. Which means the true form of the graph would be slightly here, flat out at saturation level, go a little bit back out, flat at the concentration level, and goes back down, flat at the concentration level. If I would scale it up, it would look something like this. And go on like that, because the saturation is being reached almost instantly, because the gain of this amplifier is enormous. So this is what you would expect for the graph of the